11, liquid, solids, and intermolecular forces. So, talking about intermolecular forces, that is the forces that are between all the molecules in different substances. So before we get into all the different types of intermolecular forces we have, let's go back to the 3 different phases. So we know we have gas, liquid, and water. Now, those are all our states of matter, and what are the big differences between these? So if we look at the temperature, we know that the temperature in order to reach gas is 100 degrees Celsius for water. For liquid water, it's 20, and for solid ice, it's 0. Now, you notice that there's a big difference in the densities between gas and liquid water, but between water and ice, the densities are not very different. Also, the temperature difference is not nearly as much as it is with gas than for liquid and solid. What else you notice is the molar volume. Again, very small difference between liquid and solid, but large difference between gas. Now let's look at that molecular view. When we talked about gases, we know that gases have elastic collision. They're constantly moving around. They're bouncing off of each other. They're bouncing off the walls of the container. Liquids are pretty held tightly together. They're not super compact because they take the shape of whatever container that they're in, but they're still fairly attracted towards one another. And solids are very attracted towards each other. They're very rigid, they're very, very tight, and they're constantly close together. So the solid and liquid states have much higher densities than the gas state. And they have similar densities, even though the solid is a little bit denser than the liquid. The molecules in the solid and liquid state are in close contact with each other, and you can see that the molecules in the gas state are really far apart. They don't want to be close together. They have very, very little attraction. So just thinking of attraction, you can see that liquids and solids are still fairly attracted towards one another, where gases are not. So looking at those 3 states individually. So solids. Here's a little picture of a solid. Solids are very compact and tight, ordered, structured together. So there's 2 types of solids that we look at, a crystalline solid and an amorphous solid. Oh, excuse me. Some solids have their particles arranged in an order geometric pattern, here seen on the left. These are crystalline solids. Again, high attraction, very compact and tight, want to be close together. Good example of that, when they're very orderly together, is salt and diamonds. Now, other type of solids have particles that don't really show any kinds of patterns. They're just close together in some kind of a long range, like plastic and glass. They don't have a specific pattern. Those are called amorphous solids. Liquids. Now, for liquids, we know that liquids take the shape of the container. So, they have higher densities than gases because the molecules are in close contact. They have indefinite shape because the limited freedom of molecules allow them to move around enough to get to the container walls. So since there's space between each of these molecules, if I were to take this same amount and place it into a beaker, it would take the shape of the beaker. So it has an indefinite shape. The shape is not specific. However, if this was, for example, 15 milliliters, this would also be 15 milliliters. It has a definite volume because the limit on their freedom keeps them from escaping. So because they are still attracted towards each other, they can't escape, but they have that tiny little bit of freedom in the fact that they're not super close together. They're a little bit of movement, so they can take the shapes of the containers. So that's what makes them different than solids. Solids are always going to be super, super compact and tight, so it doesn't matter where you place them. They don't take the shape of whatever they're in. A liquid has a little bit more freedom because the molecules are just far apart from one another to be able to move to the walls of a new container, but not nearly as much freedom to escape. Then if we look at gases, it's even more different. So gases, we know the particles have complete freedom. And we can say freedom of motion to be specific, since we're thinking of the motion of the particles. And not held tightly together. So that means that the particles are constantly flying around, bumping into each other, bumping into the walls of the container. There's a large amount of space between the particles compared to the size of the particles. Where have you heard that before? It's a little bit of a review when we talk about gases. Kinetic molecular theory. So the kinetic molecular theory states that the space between these particles is way larger than the size of the particles itself. So we can say that the size of the particles is pretty negligible because the space between them, since they don't want to be together, they're constantly bouncing off of all of each other, and the space that they're in is large. So the molar volume of the gas state of a material is much larger than the molar volume of the solid or the liquid state. Which brings me up to the compressibility of gases. So gases are compressible, but why? There's a lot of empty space in a beaker, right? So you can always push down and decrease the volume. Well, thinking back about gases, what happens when you decrease the volume? So if you have this container, right, and let's just say you have these particles. And then all of a sudden, like if I have a lid right here, I now place the lid down here. Now my 5 particles have a lot less space to move around. So I decrease the space, I decrease the volume. What happens to the pressure? There's higher pressure, right? Because there's just less room. There's less room to move around. So then there's more pressure because the particles are now hitting the walls more often, hitting each other more often, trying to get space between each other, so therefore the pressure increases. That's one of the reasons that gases are compressible. There's a lot of empty space, and the particles can be squeezed closer together. That makes gases compressible. Particles are not held in close contact, and they're moving around freely. So they expand to fill and take the shape of the container and will continually flow whatever space they have. So here you can see, right, you have a liquid. So these are the molecules of the liquid, and then we try to compress it. Since molecules are so closely spaced, it's not easily compressible because there's so many molecules, you can't really push it down. But for a gas, because there's so much empty space, you can easily push this down and make less room for the gas particles. Therefore, gases are highly compressible. So let's think of these attractions. So particles in different states are attracted to each other by electrostatic forces. So we know that in order for a solid, the reason that it stays together is because there's a lot of attraction going on. Those particles do not want any space between one another. For a liquid, they have some freedom of motion, but they're still pretty close, so they still have a pretty significant attraction. Then when you get to gases, those gases do not want to be close together, so the attractions are much weaker. Those attractions are called electrostatic forces. We think of the protons and the electrons of these different molecules being attracted to one another. The strength of the attractive forces varies. So for different types of molecules based off of the types of bonds they have, the elements, the polarity, the size can vary on how attracted they are towards other things or to the molecules within themselves. The strength of the attractive forces also depends on the types of particles present. The stronger the attractive forces between the particles, the more they resist to move. So a solid would be the strongest for the simplicity that we're at right now, where we're just thinking solid, liquids, and gases. A solid does not change its shape or its volume. Those particles stay just as intact as they do in any different form that you take them. Again, adding heat or things like that changes things, but just thinking at constant temperature and everything, that solid isn't changing. It's resisting any movement because it has the strongest type of attractive forces. However, in chemistry, we always think in phase changes. We always know that solids are changing to liquids and then changing to gases. Well, in order for a solid to change to a liquid, there's heat. So what is this process called? Solid to liquid. Melting, right? In order for a solid to go to a liquid, we melt it. There's another term for this, and that's called fusion. Then from a liquid to a gas, right? When you, for example, I always like to think of an ice cube. If this was my ice cube, right? And I added in heat, then do you see how all of a sudden this is now took the shape of the container? But if you counted, you have the same number, the same volume as you did before. You added heat to melt. Then if you added more heat, you would form a gas. Now see how all of a sudden all your gas particles are all over the container. They're taking completely shape of the container. You would also not have a definite volume. Some gas particles will escape. Even if you have it capped off, obviously that keeps most of the particles inside, but with any little small opening, like that little opening of the beaker, some particles can always escape. Now, that would be boiling, going from liquid to gas, and that's also called vaporization. Now, you can go the other direction. You can go from gas to liquid, but you needed to cool down and increase the pressure. That's condensation. And then cooling the liquid to get back to ice is called what? What is the process of going from liquid to solid? And then what's the process of going from gas to solid? We know from liquid to solid is freezing. And it's also fusion. It's just the opposite. Now, gas to solid, not too possible a lot of the times with different substances, but for water it is, and that's called, solid to gas, is sublimation, and gas to solid is deposition. We'll get back to these terms later on, some of them you've seen, but what I really want you to focus on is visualizing what's happening. You have your little ice cube. Once you melt it, it does not stand up like this anymore. It takes the shape of the container. Then after that, if you heat it more, those particles are going all over the place. So it's just thinking of the molecular view. You're thinking of what is happening to the actual attractions. So another way that we think of the phase changes is thinking of disorder. So when you have a solid, if we start here on the right side, you have an ordered arrangement, especially for a crystalline solid, of particles in fixed positions, and the particles are really close together. That's a lot of order. Very, very organized, you could say, right? All the books on the shelves are nice order, alphabetical, everything's great. Then you add heat, and you cause a little bit of disorder. Some shaking happened, and some of the books kind of fell out of place. Particles or clusters of particles are now free to move a little bit more, but the particles are still pretty close together. And then if you add more heat and reduce the pressure, you're in chaos. Then imagine the bookshelf was completely shaken up and the books flew everywhere. Now that would be complete disorder because you're going towards the gas state. The particles have now a lot of range of motion to go and take up the shape of the container. So you're going towards disorder from solid, liquid to gas, to more order going towards a solid from a liquid from a gas. This brings us up to intermolecular forces. Now, before we go exactly into all of the intermolecular forces that we know, what's the difference between bonds? So intramolecular forces is what we've talked about a lot already. Those are the covalent and ionic bonds that we see. The interactions within a molecule. So it's the atoms, an atom bonded to another atom, intramolecular forces. What we're talking about here are intermolecular forces. So these are the interactions between molecules, not atoms. So when you have a glass of water, you just don't have one molecule of water. You have a bunch of water molecules, and we have the liquid shape because of the way that they're attracted towards each other. Those are our intermolecular forces. Intermolecular forces are responsible for the condensation of gases, freezing of liquids into solids. So it's because of the intermolecular forces that we can actually have a phase change, that you can melt your ice, that you can heat up your water before you make coffee. It's because of these intermolecular forces overcoming one another to change the states of different substances. Now, before we get into all of the different types of intermolecular forces, we're going to take a moment to talk about Coulomb's law. So, the structure of the particles that compose a substance determines the strength of the intermolecular forces that holds a substance together, which then determines whether the substance is a liquid, solid, or gas. Again, a solid would have mostly stronger forces because they're held tightly together than liquid, then gas. The way that the structures are of the particles will help us determine what type of forces they have. At room temperature, moderate to strong intermolecular forces tend to result in liquids and solids, because liquids and solids have high melting and boiling points. It takes a lot of energy to break up those attractive forces and give those molecules freedom of motion. Weak intermolecular forces tend to result in gases at room temperature because they have low melting and boiling points. So liquids and solids have high melting points and boiling points, and gases have low melting and boiling points. The intermolecular forces originate from the interactions among charges, partial charges, and temporary charges on molecules, much as bonding forces originate from the interactions among charged particles in atoms. Now remember from in chapter 8, according to Coulomb's law, the potential energy of two oppositely charged particles decreases, becomes more negative with increasing magnitude of charge and decreasing separation. So again, R is the separation of the charges. So you think of your nucleus, that's one of your Q's, right? And then your electron. That distance is the R. So it's saying that the potential energy will go down if the charges are higher as that distance between them goes down. So we've seen that protons and electrons are attracted to each other because their potential energy decreases as they get closer together. Molecules with a partial or temporary charge are attracted to each other because their potential energy decreases as they get closer together. So potential energy of molecules decreases as they get closer together. So think of a solid and a liquid and a gas. So which one would have the lowest amount of potential energy? Thinking of what the molecules do. Well, since a solid has really no space between the particles, you would say it has the lowest amount of potential energy. Then liquid because there's a little bit more space, then gases because there's a lot of space. So as the molecules get closer together, the potential energy decreases because of the charges, and we'll see that when we talk about the specific intermolecular forces. However, intermolecular forces, even the strongest ones, are generally much weaker than bonding forces. So an ionic bond and a covalent bond, since it's just between two atoms, that's still way stronger than any intermolecular forces, because the intermolecular forces are talking about molecules. where when we're talking about an intramolecular force, we're literally talking about the attractions that are going on between just two atoms. So those are held much more tightly together and much stronger than any other intermolecular forces that could be out there, even the weaker ones. The reason for the relative weakness of the intermolecular forces compared to bonding forces is also related to Coulomb's law. So bonding forces are the result of large charges. So the charge of the proton and the electron interacting at a very close distance. So since it's two atoms together, the space between them is really small. Intermolecular forces are the result of small charges, as we shall see in the following, as when we talk about different intermolecular forces, interacting at a greater distance. So here we have our two water molecules. Now this is oxygen, and these two are hydrogens. Now notice that this bond here, the covalent bond, is way stronger than the intermolecular force between the hydrogen of one molecule to the oxygen of another. Much greater distance than the bond of 96 picometers and the intermolecular force of 300 picometers. So since the distance is much shorter for the intramolecular, the bonds, their attraction is much larger. The length of the OH bond in water is around 96 picometers. And the average distance between the water molecules that we have is around 300. So the larger distances between the molecules, as well as the smaller charges involved, because we only have partial charges, cause them to be weaker than an intramolecular force. Now, when I say partial charges, what am I talking about? We know that due to polarity, we can always assign a partial charge. So between oxygen and hydrogen, which one is more electronegative? Oxygen. So this has a partial negative charge. This is a partial positive charge. Same for the other one. Partial negative, partial positive. So this partial negative of the oxygen on the right is attracted to the partial positive to the hydrogen on the right, on the left. That is my intermolecular force. But it's not the same as a negative and a positive charge coming together like an ionic bond. It's partial charges. So again, because of the partial charges and the large difference, intermolecular forces are weaker than your intramolecular forces, the ionic and the covalent bond. Now we're going to start talking about the specific intermolecular forces that we have. First one, which exists in basically all compounds and atoms, are London dispersion forces. The attractive forces caused by these temporary dipoles are called London dispersion forces. They're contained in all. Now, what is a temporary dipole? A temporary dipole is established in every single molecule because of the fluctuations in the electron distribution in atoms and molecules. Now, what that means is we've discussed how an electron isn't just going to stay in one spot. We don't know that. No, an electron doesn't just stay in one specific spot by the nucleus or around it. Electrons are in orbitals, a region of space. We have a probability of finding them, but they're in constant motion. Now, because they're in that constant motion, they fluctuate around the atom. So sometimes they could be a little bit more on one side. Sometimes they can be distributed all evenly or on another side. Now, because they can change their fluctuations and direction, they can be more negative on one side than neutral and actually cause themselves a dipole. Now, remember, a dipole is when you have a negative and a positive side, and that fluctuation in the electron distribution can cause that. So since all atoms and molecules have electrons, they all exhibit these dispersion forces. They're in everything because every single atom and molecule can have these fluctuations of electron movement. The electrons in an atom or a molecule may at any one instant be unevenly distributed. You can imagine a frame-by-frame movie of a helium atom in which each frame captures the position of the helium's atom's 2 electrons. So this is 1. Then imagine frame 2 would have the electrons from here to here. And then for 3, you would have them here to here. So basically, at any one instance, if you were to take snapshots of helium, it's saying that One frame could show us the electrons were all the way here to the left, really close together. Another one, they were further apart, and then another one, they were on one side but not as close. That's just meaning that these electrons are constantly fluctuating. In any one frame, the electrons may not be symmetrically arranged around the nucleus, so it actually may cause the atom not to be neutral. For example, in my third frame, the helium's 2 electrons are on the left side of the helium atom. At that instant, the left side then is more negative, right? Because it's just more to the left side, and the right side is more positive. Therefore, it induced a dipole. This is called an instantaneous dipole. Induced dipole. Temporary dipole, you could say. Because it doesn't stay, right? Because again, then the electrons move this way, for example, where now you have them evenly distributed and there's no dipole that happens. So an instantaneous dipole on one helium atom induces an instantaneous dipole on its neighboring atom. So now, if we were to erase these frames, and we were just looking at one frame, and you put another helium atom next to it, what happens is that this helium will induce a dipole in another helium. Because this is now way more negative on the left and super positive on the right, it's going to force the electrons of a new helium atom to go to its left side as well, so it can become attracted, which then will force the electrons of another helium atom to also only go on its left side. So it induces a dipole on the neighboring atoms because the positive end of the instantaneous dipole attracts electrons in the neighboring atoms. The neighboring atoms then attract one another, the positive end of one instantaneous dipole attracting the negative end of another, and so on. This attraction is called London dispersion forces, short just dispersion forces. Now if we think of the relative strength of London dispersion forces. So the magnitude of the dispersion forces depends on how easily the electrons in the atoms or molecules can move or polarize in response to an instantaneous dipole, which depends on basically the size of the electron cloud, which is the size of the atom. So a larger electron cloud results in a greater dispersion force because you have a more likelihood of those electrons fluctuating. Since the electrons are held less tightly by the nucleus, they can therefore polarize more easily because they can move around more easily, causing one side of an atom to be more negative than the other. If all other variables are constant, the dispersion forces increases with increasing molar mass. Now this means that everything else has to be constant. So here you can see that for our noble gases, which are the same type of stability, as you go down, the molar masses increase. That means that they're stronger in London dispersion forces. You can notice that their boiling point increases. So what does that mean? How does that boiling point correlate with larger intermolecular forces? Well, in order to boil something, you need to break apart the particles from one another. And in order to break apart the particles, you have to break the forces. So the boiling point increases as the forces increase because the forces become harder to break apart. However, sometimes molar mass is not alone the only thing that we look at. So if we were to look at the molar masses and boiling points of N-pentane and neopentane, notice how both have a molar mass of 72.15, but neopentane has a boiling point of 9.5 degrees Celsius, and N-pentane only has a boiling point of 36.1. This is much higher than the one to the right, even though they have the same molar mass. They have the same molar mass, so we think they have the same exact intermolecular forces, London dispersion. Why do they have a difference in boiling point? What do you notice between the structures? Well, the shapes are different, right? When the molar masses are the same and you have the same number of atoms, you have to look at the shape. Because if you have to think about it again, the way that the structure is designed will show us how we can break it apart. Some may be easier than others. The N-pentane molecules are long and can interact with one another along their entire length. But because neopentane is bulky and it has a round shape, the molecules result in a smaller area of interaction between neighboring molecules, and therefore they have a lower boiling point. So here you can see the structural example of both. This long chain allows for a lot more interaction with other neighboring molecules. And because of that interaction, it can therefore have a higher boiling point. Due to this bulky shape of neopentane, they have very, very small possibilities of interacting, and therefore it has a lower boiling point and it's easier to break apart. So although we must always consider the molecular shape, molar mass, and other factors in thinking of the magnitude of dispersion forces, when we think of different elements, the electronegativity and shape, the most important is always molar mass. Thinking of molar mass as kind of a guide to how strongly things are attracted is always the safest bet. So here you can see 5 different structures: pentane, hexane, heptane, octane, nonane. Now, just by the prefixes, we know that this is 5 carbons, 6, 7, 8, and 9. So 9 carbons is going to have a higher mass. You can see that they have, therefore, the highest boiling point, which would mean the highest intermolecular forces. So a lot of the times we can just think of the molar mass for London dispersion forces. We don't have to stress too much over the shape. When we're comparing 2 of the same exact molar mass, then we think of the shape. But when we think of different ones, we think of molar mass. Now our next force, dipole-dipole forces. So this brings us up to dipoles. What are dipoles? We know that a dipole happens from the attraction of a partial positive charge to a partial negative charge. A dipole makes that happen. So basically a dipole happens because there's a difference in electronegativity going more towards the negative side, creating a partial negative charge because it's more negative now, and a partial positive charge because that side's more positive. Now, when those different molecules are attracted, a dipole to another dipole, that's when you have dipole-dipole forces. So dipole-dipole forces exist between all molecules that are polar, since we know that a dipole is in a polar structure. Polar molecules have electron-rich regions and electron-deficient regions. So if we look at these examples of acetone here, you have your oxygen, carbon, 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 and all the hydrogens. Now, since oxygen is the most electronegative, the dipole goes towards the oxygen. Which makes the carbon side more positive and the oxygen side more negative. Well, if I put 2 acetone molecules together, which in a big jug of acetone you have a bunch, the oxygen becomes attracted towards the carbon of the other, which would then become attracted towards the carbon of another one, and so on. That force is a dipole-dipole force, because the partial negative of one structure attracts itself to the partial positive of another molecule. Now again, it's different molecules, it's not bonds. That creates a dipole-dipole force. Notice that acetone is super electron rich in the oxygen and electron poor in the carbon and hydrogen. Now this stays and becomes a permanent dipole that can interact with another acetone molecule, and so on. The positive end of one permanently attracts the negative end of the other. So it's different from our dispersion where that was an instant dipole because that changes. This is a permanent dipole. Here you can see another little picture that the space-filling model, knowing that our attractions are constantly occurring between the partial negative and the partial positive of the neighbors, being a permanent dipole. Now thinking of how we can compare them. So we know that all molecules, including polar ones, have dispersion forces. We know that the London dispersion forces increase with increasing molar mass. Now, polar molecules have an addition dipole-dipole force. So we can have a molecule that can just have London dispersion, or you can have a molecule that can have London dispersion and dipole-dipole. The additional attractive forces is therefore going to do what to the melting or the boiling point? If you have dipole force, you have a really strong attraction between the negative end of one to the positive end of another molecule. Is that going to increase or decrease the ability to melt or boil it? It's going to make it harder to melt or boil, so the temperature of the melting and boiling point is going to increase. So look here at ethane and formaldehyde. Now, we think of carbon and hydrogen. We know the electronegativity difference gives us nonpolar. So this just has dispersion forces. Formaldehyde has dispersion, and because of the polarity of the oxygen, we also have dipole-dipole. So we know that ethane would be much easier to melt than formaldehyde. If you then look at the boiling points, you can see that formaldehyde is polar and has a higher melting and boiling point than the nonpolar ethane, even though both of these compounds have almost the same exact molar mass. So then here we're learning more about how to look at the structures when they have the same mass, but if they have more forces, then their boiling and melting points are going to increase. The polarity of molecules is also important in determining the miscibility of a liquid, which means the ability to mix without separating into two states. In general, polar liquids tend to be miscible with water, while nonpolar liquids are not. So we think of polar mixes with polar, and nonpolar mixes with nonpolar. Another way to say that would be like dissolves like. So miscibility is the ability to mix without separating into two states. So this is very true for water, which is really polar. So in general, polar liquids tend to be miscible with water because they don't separate into two states, while nonpolar states are not. When you take pentane, which is nonpolar, it does not mix with water. But water and oil, which is also nonpolar, do not mix. But oily hands or oily stains on clothes cannot be washed either with plain water. So these are all little examples of how, for example, if you get oil on your clothes and it doesn't matter how much you wash it, it does not go off, because just with water, stains don't leave because it's polar and nonpolar. So like dissolves like, nonpolar will dissolve in nonpolar, and polar will dissolve in polar. Let's put that to an example. So which of the following molecules will have dipole-dipole forces? So carbon dioxide, right, is CO. Now if we think of, we know they all have dispersion. Is this a polar molecule or a non-polar molecule? Carbon dioxide, we know the dipoles cancel each other out, so this is non-polar. So does it have dipole-dipole forces? No, does not have dipole-dipole forces. What about CH2Cl2? So we have CHHCl. Well, we know that these are nonpolar, carbon and hydrogen. We know chlorine is really electronegative. The shape is a tetrahedral shape. So would this have polarity or not polarity? Well, the two chlorines all go towards one side, so this is a polar molecule, so it does have London dispersion forces. What about our last one, methane, CH4? Would this have London dispersion forces or not? Geometry is tetrahedral. All the H's are the same this time, so there's not one more electronegative element pulling the electrons in one direction. So this is nonpolar. Therefore, it does not have London dispersion forces. All right, we got two more intermolecular forces before we move on from this section. The next one is hydrogen bonding. Now that term bonding always gets confusing. This is not an intramolecular force. It's not a bond. Again, it's still the attraction between different molecules. So polar molecules that contain hydrogen atoms that are directly bonded to small electronegative atoms, mainly fluorine, oxygen, and nitrogen, exhibit an intermolecular force called hydrogen bonding. For example, HF, NH3, H2O. These are all have a hydrogen that's directly connected to one of the three most electronegative elements, which can be attracted to another hydrogen of one of the three most electronegative elements, creating an intermolecular force that's called hydrogen bonding. The hydrogen bond is a sort of super dipole. Hydrogen and these three electronegative elements, if you look at the periodic table, is a really, really, really strong difference in electronegativity. That's why it's basically saying like there's a super large dipole-dipole force. The large electronegativity difference between hydrogen and any of these electronegative elements can cause the hydrogen atom to have a fairly large partial positive charge within the bond, while the fluorine atom would have a very large partial negative charge. And this accounts for ammonia and water and any other hydrogen-type bonding molecules. So if this was HF, so this is my fluorine and this is my hydrogen, the hydrogen bond occurs between the really partial negative fluorine to the really partial positive of the hydrogen. Because this is a hydrogen to one of the three most electronegative elements, the intermolecular force is a hydrogen bond. Now again, this still has dipole-dipole forces because it is a dipole, and it has London dispersion. But the most strong force possible here is the hydrogen bonding. So another example here. So hydrogen should not be confused with chemical bonds. Chemical bonds occur between individual atoms within a molecule. But hydrogen bonds, like dispersion and dipole-dipole, are intermolecular forces that are between the molecules. A typical hydrogen bond is only 2 to 5% as strong as a typical covalent bond. Hydrogen bonds are the strongest of the three intermolecular forces so far. So we have a hydrogen bond, dipole-dipole, then dispersion. But a hydrogen bond is limited to a hydrogen being attracted to the fluorine, nitrogen, or oxygen of another molecule, not within the same molecule. So when you have different compounds and you're comparing the strength of the intermolecular forces, you can see that the boiling point will be much higher when you have hydrogen bonding than when you just have dipole-dipole. So here, sorry that this is a little bit of a blurry picture, you can see that because of hydrogen bonding, the boiling point of water is a lot higher than the boiling point of a lot of other of these substances. 100 degrees Celsius is the largest one compared to the hydrogen that's bonded to some of these other ones. Because that's not the intermolecular force of hydrogen bonding, these are just covalent bonding between a hydrogen atom and other substances. So then now we are to another example. So let's think of choosing the substance in each pair that is the most soluble in water. So come back to thinking like dissolves like. So CH3OH, methanol. Is that polar or non-polar? That is polar. And then we have CH3CHF2. Okay, is that polar or non-polar? It's not as easy for me to see. This was really easy because I have the oxygen. Here I have the fluorine, so I'm going to assume it is polar, but I'm going to draw this out too. Carbon, carbon. And then I have a hydrogen and a fluorine and another fluorine. So would you think this is polar or non-polar? And this is very polar. The dipole is going just to the direction of fluorine. So, which one between these two would be more soluble in water? Since we know that this has what type of forces? They both have London dispersion forces. They both have dipole-dipole. Now, do they have hydrogen bonds? Now, this does not have H-bond forces because the hydrogen is not directly bonded to one of the most electronegative elements. So, the more soluble of these is methanol because it has the strongest intermolecular forces. Now, next one. Since we only have carbon and hydrogens here, we know this is non-polar and we only have dispersion forces. Then we have CH3Cl. Now this has a dipole going towards chlorine, so we have dispersion and we have dipole-dipole, not hydrogen bonds. So this is more soluble. Is it more soluble in water? What I circled was the one that's stronger. So we know methanol is the more stronger one because it has higher intermolecular forces between those two. And CH3Cl is more soluble because it is more strong because it has the higher intermolecular forces. Now, which one do you think would be actually easier to dissolve in water? Well, water, right, has what type of intermolecular force? Think like dissolves like. So for water, we're thinking dipole-dipole and hydrogen bond. So since methanol is the most comparable to water, it will dissolve more easily, and CH3Cl as well because it has more of the similar intermolecular forces than the nonpolar substance. Now we've made it to our last intermolecular force, the ion dipole force. Ion dipole occurs when an ionic compound is mixed with a polar compound. It is essentially really important in aqueous solutions of ionic compounds. So for example, think of sodium chloride, which we use a lot. We mix that into water. Now NaCl is aqueous, so we know that splits up into sodium ion and chlorine ion. Well, if you put it into water, those water molecules are going to hydrate those ions, but they're not going to hydrate them the same way. Since sodium is positive, the negatives of the oxygens in the waters are attracted to sodium. That attraction is an ion dipole. And the negative chlorine becomes attracted to the positive hydrogens, which is also an ion dipole. The positive sodium ions interact with the negative poles of water molecules, the oxygens. The negative chloride ions interact with the positive poles of the hydrogens in water. The ion dipole forces are the strongest of the types of intermolecular forces. So we have ion dipole, hydrogen bond, dipole-dipole, and then dispersion. So when you're thinking of which substances are the strongest, you always first want to find what type of intermolecular forces that you have. If you then have similar ones, then you're thinking of the masses between them. And then if they have the same mass, then you think of the structure. So the dispersion forces are present in all molecules and atoms and are generally increasing with increasing molar mass. These forces are always really weak in small molecules, but can increase in larger molecules. Dipole-dipole forces are present in all polar molecules because every polar molecule has a dipole. Hydrogen bonds, the strongest of the intermolecular forces that can occur in pure substances, second strongest to ion dipole, are present in molecules that have hydrogens bonded to fluorine, oxygen, and nitrogen. So we saw in that previous example how this was not a hydrogen bond because the hydrogen was not directly connected to fluorine. Ion dipole forces are present in mixtures of ionic compounds and polar compounds. These forces are really strong and really important when it comes to placing ionic compounds in aqueous solutions. So ending this section with a practice little group check. So arrange the following in order of increasing boiling point. So what do we have here? We have helium and neon, 2 oxygens, chlorine, and then a compound. Now, increasing molecules means strongest intermolecular forces. The stronger the force, the harder it is to break up, the more temperature it takes to boil. So what are my molar masses? Let me get out my periodic table, and I'm going to just first look at what forces I have. Well, for helium and neon, I just have London dispersion. And I know helium is the least heavy, so helium would go first as least, right? Lowest boiling point. Then it would be neon. Then I look at oxygen 3, oxygen 2, and chlorine. Well, chlorine to chlorine is a nonpolar, so it just has dispersion. And chlorine is around 70 grams. Okay, well, oxygen and oxygen. Oxygen also nonpolar, and it is around 32. So then I would have oxygen 2. What about O3? Does O3 have polarity? This is also nonpolar. Well, 16 times 3 is 48, so we would have O3, then Cl2. We know this structure is polar, and then the second structure here for the order of increasing boiling point. Arrange the following in order of boiling point. So we have hexane, so that's nonpolar. Then we have a chlorine, so then we have a polar structure. Then we have a bromine, so another polar structure. Then we have an H bond. So I know this is highest boiling point. This is lowest. Now, what is the difference between the chlorine and the bromine? Bromine is heavier. But is chlorine more negative? Is chlorine more electronegative? Does it have a stronger dipole? Yep, so then it would be, this would be highest, then with the chlorine, then the bromine, and then the nonpolar hydrocarbon. Awesome, so that ends our long little chat of intermolecular forces and the phases of change to bring us up to the next part of the chapter, looking at, again, figuring out the different structures, looking at what type of forces they have, then their masses, and then what the structure looks like. The stronger the forces, the more they want to be together, so they're harder to break up, which means that the temperature to break them up is going to be really high. So stronger forces, higher melting and boiling point.